So now we want to solve this killing vector equation. So the first thing that we'll do is, well, d alpha zeta beta plus d beta zeta alpha is equal to 0. And that means that d lambda acting on d alpha zeta beta plus d beta zeta alpha is also equal to 0. And now what I'm going to do is I'm going to take exactly the same equation and I'm just going to relabel indices a little bit. So I'll have d alpha, and now I will have d lambda zeta beta plus, that's a beta, d beta zeta lambda is equal to 0. Okay, and you can see why these are 0. So I'm basically taking a derivative of the killing vector equation, but the right-hand side is naught, and the derivative of naught is still naught. Now I'll have a d beta, and we'll have d lambda zeta alpha plus d alpha zeta lambda is equal to 0. Let's call this equation 1. We will call this equation 2, and we'll call this equation 3. Now, there's something that I want to draw your attention to. So look at this term, d lambda, d alpha, zeta beta. This is exactly the same as this term. The indices of the derivatives are alpha and lambda, and we're differentiating zeta beta. Next, look at this term. D lambda, d beta, zeta alpha, and that's the same as this term. We're differentiating zeta alpha, and we're taking a beta and a lambda derivative. And of course, those partial derivatives commute. And then take a look at this term. We're differentiating zeta lambda with respect to alpha and beta, which is exactly the same as this term. We're differentiating lambda with respect to alpha and beta. So what we can now do is we can start to consider some linear combination of these equations. So let's take 1 plus 2. So we add the first two lines and then minus 3. So can you see what's going to happen? If you add the first two lines and subtract the third line, well, this red term will cancel against that red term. This green term will cancel against that green term. You'll only be left with the blue terms, and the two blue terms are equal. So after adding them, you'll get a 2. You'll get d lambda, d alpha, acting on zeta beta is equal to 0. So this is the equation that we've got now. Now, why is this a nice equation? Notice that lambda is anything, and alpha is also anything. So that means, so remember that lambda stands for a d by dx lambda, and the alpha term is for a d by dx alpha. So that means if I take any two derivatives with respect to the coordinates, I get 0. So what this boxed equation in black is telling me is that I've learned that zeta beta is linear in the coordinate. So it's linear in the coordinate. And that's a fantastic insight because what it now tells me is, well, I can write down exactly what zeta alpha is. So zeta alpha will be, I may have a constant term that's perfectly consistent with the boxed equation. And then plus, I've got some coefficients. I'll call it omega alpha beta into x beta. So I wrote down this equation in the red box because of the equation in the black box. The equation in the black box forces the equation in the red box. Zeta must be linear in x. And now I don't know what these coefficients A alpha and omega alpha beta are, but what I can do is I can take this killing vector and I can plug it into the killing vector equation. So let's see what would I get. In fact, you know what? I'm gonna change the name of this coefficient, this beta. I'm gonna change it to a rho. It's a rho. Okay. So if I calculate d beta zeta alpha, what will I get? And I'm going to use the fact that d beta on x rho, well, what is this? This is dx rho dx beta. And you know that this is going to be 1 if rho is equal to beta, otherwise it'll be 0. So I'll just get a Kronecker delta. So if I differentiate d beta on zeta alpha, acting on the a, I just get a 0, so I don't have to worry about that term. Then I'll get an omega alpha, and I'll have a delta rho beta. So it'll set the rho on the omega equal to a beta. So d beta zeta alpha is just omega alpha beta. And then obviously, just by relabeling indices, d alpha zeta beta will be equal to omega beta alpha. So the killing vector equation, which tells me that d beta zeta alpha is equal to 0 and d alpha zeta beta is equal to 0, what does the killing vector equation imply? If I plug these in, it tells me that omega alpha beta plus omega beta alpha is equal to 0. So this is now the solution to my killing vector equation. It's those two red boxes. Zeta alpha is A alpha plus omega alpha rho x rho, and omega alpha beta plus omega beta alpha is equal to 0. Let's try to get some insight into whether this makes sense or not. And we're going to get some insight just by counting parameters. So let's say counting parameters. And I'm going to do this count in d dimensions. Okay, so what does that mean to be in d dimensions? For example, if I've got x mu, then mu would go over 0, 1, all the way up to d minus 1. So if I look at a alpha, well, alpha runs over d values, so there's a total of d different a alphas I can have. How many omega alpha rho's can I have? Well, alpha rho each run over d values, so this looks like a d by d matrix, but it's antisymmetric. That means the elements on the diagonal vanish. So we would have started off with d squared elements, but the diagonal elements vanish, so let me subtract off d. And then because it's antisymmetric, the elements above the diagonal are minus the elements below the diagonal. So once I specify the elements above the diagonal, the elements below the diagonal are specified. So the number of independent components, I need to divide this by 2. So this is just d times by d minus 1 over 2. And this is already pretty good to get an idea of what's going on. Let's say d is equal to 4. Then how many A alphas will we have? We'll have 4 of them. How many omega alpha rho's will we have? Well, 4 times 3 is 12, divided by 2 is 6. And if you remember, there are a total of 4 translations. So the A alphas correspond to just a translation. And indeed, look at the red box, the first red box. Zeta alpha is equal to A alpha. This would be just adding a constant onto each coordinate. Remember, our coordinate transformation, where did we write it? X tilde mu is equal to x mu plus zeta mu. So let me just remind you of that. X tilde mu is equal to x mu plus zeta mu. This is the equation you should have in mind. If we just take the A alpha, it's like x tilde mu is A mu, x mu plus A mu. We've just done a translation of the coordinate. So that works perfectly. And then these 6 parameters here, the 6 should remind you of 3 rotations and 3 boosts. So these are the Lorentz transformations. 3 rotations and 3 boosts. So by solving the Killing vector equation for the isometries of Minkowski space, we've recovered the Poincare group, translations, and Lorentz rotations. Okay, we'll continue in a moment.